recording. So today I wanted to talk about Quillen functors. Maybe derived functors, but I'm not sure that they will get to that. So let me just sketch the general idea behind Quillen functors. So we already defined what model category is, and now we want to consider a category of small model categories. And so we have objects, and now we need morphisms. As opposed to what one might expect, the morphism between model categories, well, at least this notion, does not require a functor to preserve all the model structure. It requires a functor to preserve only half of model structure. So let me sketch the definition. Assume that we have two model categories M and N, and we have an adjunction. F is a left adjoint functor, F prime is a right adjoint functor. Then we require Quillen functor to preserve cofibrations and trivial cofibrations. And dually, we require the right Quillen functor, which is the right adjoint, to preserve fibrations and trivial fibrations. And so we see that on M and N, F and F prime are not homotypical functors, meaning that they do not preserve in general all weak equivalences. However, it is true that they become homotypical functors when restricted to deformational retracts of categories M and N respectively. So F restricted to the subcategory of cofibrant objects in M is a homotypical functor. And conversely, F prime restricted to the subcategory of fibrant objects in N is a homotypical functor. Okay, so now I'll explain why Quillen functors are so good in this context. The fact is that any Quillen functor can be in a homotypically unique way approximated by a homotypical functor. What does it mean? So let F M to N be left Quillen functor. Then there is a pair QA where Q is a functor in the same direction, which is additionally homotypical, meaning that it preserves weak equivalences. And A is a natural transformation which goes from K to F. So this is why it's called the left approximation. Okay, and such approximations are homotypically unique in a sense that I will explain later. But I can briefly state what does it mean. Well, basically it means that this pair Ka is homotypically. Oh, no, I don't think that they are. No, let's just let me just state that K is homotypically unique, whatever that means. And later I'll explain what it means exactly. Additionally, as it turns out, a composition of Quillen functors is also a Quillen functor. So if we have two composable Quillen functors, left Quillen functors, of course, then their composition is also a left Quillen functor. Moreover, the same holds for left approximations of left Quillen functors, namely if we have the left approximation of F1 and the left approximation of F2, then we can form a homotypical functor like this, and it is a left approximation of the composition. So the natural transformations A2, A1 is defined using the following diagram of natural transformations. So we have the square like this. And the diagonal of the square is precisely the natural transformations, natural transformation A to A1. So yeah, this is another useful property for Quillen functors, and of course, Boole for right Quillen functors. Also have that if we have the right approximation like this and the right approximation like this, then we have the right approximation of the following form. Sorry, the right approximation, so there we should know this. And also, if we have a Quillen pair, then we have an induced adjunction on the homotypical categories, model categories. So assume that we have equivalent pair like this. And let K8 be left approximation of F. And K prime A prime be a right approximation of F prime. Then there is a derived junction, which looks like this. So remember that Quillen functors do not preserve equivalences. So in general, they do not descend to functors on homotypical categories. However, their approximations are homotypical functors, and therefore they induce functors on homotypical categories of M and N. And this adjunction is natural in K and K prime, meaning that if we have another pair, say K1, A1 and K1 prime, A1 prime, and the morphism of such pairs, then we have a transformation between these adjunctions. And I want to finish this introductory part with a short discussion of Quillen equivalences. So Quillen equivalents are a special kind of Quillen adjunctions, which basically induce upon homotypic category of homotypic categories of model categories. Consider an adjunction. Then the following conditions are equivalent. So first, sorry. So first there is a left approximation of F. Such that K is homotypic equivalence of homotypical categories. Well, this condition actually implies that for any other left approximation of the functor F, we in fact have the same. So K tilde will be also a homotypic equivalence of homotypical categories. This will follow from the fact that left approximations are homotypically unique, which I will explain later. And we also have well, this is just the dual version of the first part, namely that if we have a right approximation of f prime, then it also induces homotypic equivalence of homotypical categories. Okay. So this actually can be improved, and we state that second part is that there is a pair of approximations. So we have K from the left to F and K prime, sorry. Yeah. So K prime, A prime from the right. Such that model categories are mutually inverse equivalences, homotypic equivalences of homotypical categories. Well, another way to formulate this is that, yeah, and so this also implies that for any pair of approximations, this is the case. So another way to state this would be to say that if we have a left approximation of the functor f, then the homotypization of the functor k is an equivalence of categories. And of course, we have the dual statement for the right approximation of the right Quillen factor. And another thing that can be stated is that for some pair of approximations, like this, and the homotypical versions of these functors I give mutually inverse equivalences of homotypic category of M and homotypic category of N. So F is called left Quillen equivalence under any of these conditions, and F prime is a right Quillen equivalence. And so we can also state a necessary and sufficient condition for a Quillen junction to be Quillen equivalence. It is called the Quillen condition. It states that, let, as usual, f and m prime be a Quillen junction. Then it is a Quillen equivalence if for any cofibrant object X and C and any fibrant object Y in N, the map X to F prime Y is a weak equivalence if and only if the map from Fx to Y, which is adjoint to this map, is a weak equivalence. Okay, so this was sort of an introductory part. I explained what Quillen functors are supposed to be. Now I will try to give more detail to all of this. So I'll start from the notion of homotypical uniqueness. As promised, approximations to Quillen functors should be homotypically unique, and to explain what this means, I need to explain what homotypical uniqueness is in arbitrary homotypical category. So we start from notion of categorical uniqueness. Which is just a part of ordinary category theory with no extra structure. So first of all, let G be a category, then it is contractible if either of the conditions are satisfied. So the functor, the unique functor, which goes from G to the category consisting of one object and one morphism, is an equivalence of categories. And based on this definition, we get the second equivalent condition, which states that G is supposed to be a groupoid, which is not empty, and such that the Hom set between any two objects consists of a unique morphism, a unique isomorphism. Okay, so now I can explain what does it mean for a family of objects in a category to be unique. So assume that Y is a category and I is a set such that I is not empty. and assume that yi is a family of objects in the category y for all I in the set I. Well, we say that this family consists of canonically isomorphic objects, or that this family of objects is categorically unique if either of the two conditions are satisfied. So the full subcategory of y spanned by this family of objects is contractible. I think I better use the term categorically contractible here, so as not to mistake it for homotopically contractible homotypical categories. I should say is categorically contractible, meaning that between any two such objects there is a unique isomorphism. And another way of stating it is that categorically full subcategory of y, meaning, yeah, so spanned by, I finished this phrase, spanned by yi, is categorically contractible. So the categorically full subcategory just means that we take not only the full subcategory spanned by yi's themselves, but actually by all objects which are isomorphic to yi's. So okay. So now let me just remark that additionally, it could be seen that for any category C, the full subcategory spanned by initial object or terminal object is either empty if there is no such object, or categorically contractible. So this sort of gives an idea how to prove, at least sometimes, that something is categorically contractible, or that something is categorically unique. So this is basically the same as we prove in any category that the initial and terminal objects are unique if they exist. So categorical uniqueness can be established by observing that this family of objects consists of initial or terminal objects in some sense. So this could be stated in the following informal way. Some objects in the category Y, in the category X, are unique up to unique isomorphism. Because they satisfy certain initial or terminal universal property. So more rigorously, this could be stated in the following manner. These objects satisfy initial or terminal property in the category of all objects of X with certain maybe implicit structure. However, it should be noted that not all results on categorical uniqueness are of this form. So, for example, we have clearly categorically unique object, which is a co-product with a product of two objects. However, it is not true that this object comes as the initial object in a category of all diagrams of this form. So yeah. So now we can move on to the homotypical version of the concept of categorical uniqueness, which will be very useful for us when describing approximations to Quillen functors. So So let G be a homotypical category. We say that G is homotypically contractible if either of the two conditions are satisfied. So either the functor from G to the category with an object in one morphism is a homotypic equivalence of homotypical categories where this has a trivial homotypical structure. And the other way is to deduce that 342 property implies a different characterization, namely that all morphisms in G are weak equivalences, and for any two objects x and y in G, x is weakly equivalent to y, which means that there is a zigzag of weak equivalences between the two. So now we can formulate a version of a notion of categorical uniqueness, but in homotypical setting. So let Y be a homotypical category. I is a set which is not an empty set, and we say that a collection of objects in this homotypical category is canonically weakly equivalent or homotypically unique if the following condition is satisfied. So homotypically full subcategory of Y spanned by these objects meaning the full subcategory spanned by the set of objects, and additionally all weakly equivalent ones. So this homotypically full subcategory analogously should be homotypically contractible. Well, it's homotypically contractible. Okay, so now we can state what does it mean for an object in a homotypical category to be homotopically initial or homotopically terminal. So let Y be a homotypical category and Y be an object of Y curly, then Y is homotypically initial or terminal if there is a zigzag natural transformations which looks like this. This is for homotypically initial object, and quite expectedly, if we go in the opposite direction, we obtain the condition for homotypically terminal object. So, what does all this mean? Well, first, this CSTY is just a constant functor which goes from Y curly to Y curly, and it just sends all objects to Y, all morphisms to the identity morphism of Y. This functor is, well, just the identity functor on Y. This ellipsis is a zigzag of natural weak equivalences. So recall that we have a notion of natural weak equivalence inside of the functor category between two homotypical categories. Yeah, and finally, F is such a functor that, well, not a functor, a natural transformation, such that its component on Y is a weak equivalence, Y curly. So it is not hard to see that there is a following property of homotypically initial and terminal objects in a homotypical category, namely that any homotypically initial object in Y curly becomes just the initial, becomes an initial object in the homotypic category of Y curly. Same for homotypically terminal objects. And so additionally, it can be shown, so from the 6 for 2 property, it follows that if so it follows that if Y is an object in Y curly and it is homotypically initial or terminal, then Y prime in Y curly is homotypically initial or terminal if and only if Y is equivalent to Y prime. That means that we have a class of weakly equivalent objects which are all homotypically initial and terminal, or terminal, and this is precisely all such objects in our homotypical category. So this in particular implies that in any homotypical category, there is a full subcategory spanned by the initial terminal objects, which is either empty or contractible, or homotypically contractible. So just in the case, or like in the case of ordinary category, it's convenient to prove uniqueness using homotypically initial or terminal objects. So let me state somewhat an informal statement that a family of objects in X is typically unique if they satisfy homotypically initial or terminal universal property And we can further formalize this by stating that this means that these objects are homotypically initial or terminal in a homotypical category of all objects in X with additional structure, some additional structure. So now I will formulate, well, not so hard proposition, which I will not prove, but maybe in some subsequent talks I will give a proof. So let X be a homotypical category and X1 and X2 be some subcategories in X. We additionally require that either so X1 or X2 is categorically contractible. Yes, sorry. So a map from X1 to X2, which is a morphism in X, is homotypically initial or terminal in a category, well, in a category of X1 over X2, meaning that it consists of, well, all so objects suggest morphisms from X1, which belongs to X31, to X2, which belongs to X32, and morphisms suggest squares where the upper row belongs to morphisms in X1 and the lower row, the bottom row belongs to morphisms in X2. Such squares. And so this thing here obviously inherits structure of homotypical category because, well, a morphism is a weak equivalence if each of its components is a weak equivalence. But yeah, so a morphism between two objects from these two different subcategories is homotypically initial or terminal in this homotypical category if and only if X1 to X2 is homotypically initial or terminal for homotypical categories x1 over x2. So it is important that here we have straight x1. So this is just a usual undercategory of an object. And for terminology, we have an opposite thing. So we have the following equivalence. Well, it is not that hard to prove. The basic idea is that since x1 or x2 is categorically contractible, there is like a unique isomorphism. And going from there, it is easy to see that, well, you can see that it is indeed the case that we only need to consider morphisms from x1 to x32, and not all morphisms from all objects of x1, of x31. Well, the basic idea is that categorically contractible category can be replaced by one of its objects without losing much information. Okay, so now let me give a more formal treatment of Quillen functors. So here's the definition. Assume that M and N are model categories, and assume that we have an adjunction like this. Then with an adjunction is an adjunction such that the two conditions are met. F is a left Quillen functor, meaning that it maps cofibrations to cofibrations and trio cofibrations to trio cofibrations. And F prime is a right Quillen functor, meaning that F prime maps fibrations to fibrations and trio fibrations to trio fibrations. So Quillen functors have the following elementary properties. So the first one is that an identity functor on any model categories, both left and right Quillen functor. The second part is that if F is a left Quillen functor, then for any, well, any, but they're all isomorphic, so it's not that important. But for any right adjoint of F, it follows that f prime is a right Quillen functor. And obviously we have a dual statement, namely that if f is a right Quillen functor, then any of its left adjoints is also a left Quillen functor. Well, the third part states that an opposite of a left Quillen functor is a right Quillen functor. And finally, composition of any two composable left Quillen functors is a left Quillen functor. Well, let me give a short proof of this. So the first part is clear because obviously it maps, well, it does nothing on the maps, so it obviously maps cofibrations and trivial cofibrations to cofibrations and trivial cofibrations. And so the first part is clear. The second part follows from the fact that vibrations and trivial vibrations could be described using lifting properties. And so, well, you basically just consider a lifting square, you apply the functor, you look at the adjoint morphisms, and you obtain a lift in a square where you have like opposite maps. So if you had like trivial cofibration, then it's replaced by trivial vibration and so on. And finally, the third part, yeah, not finally, but the third part follows from the definition of opposite model categories. So as you recall, weak equivalences remain the same and vibrations and cofibrations change places. Finally, the fourth part is also clear because you just look at the, well, because cofibrations are mapped to cofibrations and then again mapped to cofibrations. So let me make a quick remark here that for an adjoint pair, it is sufficient to check that only one of the functors is a Quillen functor. which is usually easier than to check it for both. And then you can just use a jointness to establish that you have, in fact, have a Quillen junction. Okay. And so let me state another key property. Quillen junctions. Namely that if we have a Quillen pair, Quillen junction, then if restricted to the subcategory of cofibrant objects is a homotypical functor, and the second part states that f prime restricted to subcategory of fibrant objects is a homotypical functor. Let me prove this. Well, this follows directly from Ken Brown's lemma, which states that if some functor from a model category to a relative category maps trivial cofibrations, for example, between cofibrant objects to weak equivalences, that means that it maps all weak equivalences between cofibrant objects to weak equivalences. So this is precisely what we need to establish the fact that F restricted to the subcategory of cofibrant objects is homotypical. Okay. So now let's move on to approximations. So as was stated above, one of the key properties of Quillen functors is that they have homotypically unique approximations. Now we know what is the meaning of the words homotypically unique. So it only remains to find the correct categories where we establish this homotypical uniqueness. So let me define two auxiliary categories which are used to define left and right homotypical approximations. Left and right approximations to Quillen functors. Well, basically to any functor between two homotypical categories. So consider a functor f between M and N, which are both homotypical categories. We consider well, let me adhere to my notation, so I'll call them y and x. X and y. So we define a category like this. So this is a subcategory, a homotypical subcategory of homotypical functors between two homotypical categories, and it is an overcategory of functor F. And we also have another category of functor F, not the same form. So just by definition, objects here are pairs Ka, where K is a homotypical functor from X to Y, and A is a natural transformations from K to F. Well, in this case, A is a natural transformation from F to K. And so the morphisms here are the following. Maps of pairs, which look like this. So so these are natural transformations. Key from K1 to K2, which fit into triangle of this form. And to obtain a subcategory of weak equivalences in this homotypical category, we just need to consider such T that they are natural weak equivalences. So this is the definition of this category and homotypical structure. So now we can move on to approximations. Of Quillen functions. So once again, let F and F prime be a Quillen junction. We define left approximation of F is a homotypically terminal object in an overcategory of F. Well, it's quite natural. We choose like the closest thing in this homotypical category to the object F. Right approximation of F is a homotypically in the undercategory of this category. So once again, the idea is quite clear. We pick the closest thing. And from the properties of homotypic initial and terminal objects, we see that if left to right approximation exists, because initial and terminal objects are homotypically unique. So now it remains to show that they in fact exist. And an instrument that will help us is the fact that we can consider retractions to the subcategories of cofibrant and fibrant objects. So F and F prime piece before, and we have left, which consists of functors deformation. So and these two deformations help us to define left and right approximations. So the left approximation will look like this. It is a left approximation of F. And the right approximation of F prime looks like this. So So let me prove that this left part is in fact the left approximation of F. Consider this pair FQ, Fs. This category here. And we need to show that it is in fact homotypically terminal. So observe that for any object in this over category, there is a zigzag in this over category, which looks like this. So this is AQ, and This one here is KS. And AS here is, as usual, defined by means of the following commutative square. So the diagonal here is the desired natural transformation AS. And this zigzag that we discovered has three properties that imply homotypical linearity of FQ Fs. So the first property is that the zigzag above is functorial in the pair Ka. Second part is that Ks is a natural equivalence, which is also quite clear because S itself is a natural equivalence, and A is a functor. And finally, we observe that if Ka is equal to Fq Fs, this implies that Aq is equal to Fsq. Is a weak equivalence. So these three properties together establish precisely what we need to show that we in fact have a homotypically terminal object. Let me briefly recall these requirements. So we required that we have transformation between the identity and the identity functor and the constant functor, and basically that is precisely what we constructed. So we have a zigzag where one part of the zigzag is a natural equivalence. One part of the zigzag is a weak equivalence, weak natural equivalence. We start from the constant functor, and we finish with the identity functor. And when restricted to our supposedly terminal object y, we should have a weak equivalence. And this is precisely what we have. So this shows that this pair is indeed a left approximation. Okay. So now let me say something about frontal composition. So if we have two not necessarily homotypical functors between homotypical categories, this means that we can consider a composition functor, which works like this. So we take the over categories of homotypical functors over F1, take a product with the over category of homotypical functors over F2, and we map all this to the over category of homotypical functors over their composition. And how does it work? Well, it's not that hard to describe. We just take a pair of consisting of functor and natural transformation, and we map this pair to the composition where the composition of functors is once again defined using a commutative square of natural transformations. So analogously, we define a functor of of a product of under categories. So we have a functor that goes like this. Okay. What is the usefulness of this notion of composition or functor composition? Well, the key thing here is that both composition functors are homotypical. And so that's the first one. And the second observation is that one homotypically initial terminal object is mapped to. Then this implies that any homotypical initial terminal object is mapped to homotypical initial terminal object. This simply follows from the fact that these functors are homotypical, and we have like this batch of homotypical initial or terminal objects, which are all linked by weak equivalences. And so if you map one to another batch of homotypic initial terminal objects, it means that all these equivalences are also mapped to weak equivalences, and so all homotypic initial terminal objects are mapped to homotypic initial terminal objects. Okay, so after seeing this, we can formulate the following important proposition. So assume that we have two Quillen junctions, one between M and N, and the second one between N and P. So so first of all, observe that we have, so we can compose and we obtain a Quillen junction, but this was done before. What is not trivial is that each composition on the left approximation to F1, the left approximation to F2 gives a left approximation to their composition. And the third part is just the dualization of the statement, namely that if we take right approximation to the right Quillen functors, then their composition is the right approximation to composition of right Quillen functors. So let me prove this. Oops. So the first follows from elementary properties, and it's not that interesting. And because we established that composition factors described above are homotypical, the second part is sufficient to prove only for approximations. And since we're considering Quillen functors, we sort of have a canonical approximation, which was described above, namely the approximation constructed from co-fiber replacement on model case-series. So let's consider this one. So let Q1 S1 and Q2 S2 be deformations to MC and of N on to MC. Then we have between the following two functors between M and P. So we take a composition of this pair. And we have a map which is this one. And so this is a morphism. So this is a morphism in the over category of this form. And the only thing we really need to prove is to show that but this is quite clear because well, second, yeah. So this is quite clear because S2 is weak equivalence, and yeah, well, so this is a weak equivalence. And yeah, in the composition, F1 Q1 is a homotypical function. So what we get here is also a weak equivalence, which means that this thing right here is a left approximation of the composition F1, F2 by the previous proposition, where we established that if we consider a pair like this, it is always a left approximation. And this thing here is a left equivalence, which means that it is also a homotypically terminal object in the over category, which means it is also a left approximation. So and this proves the proposition. Okay, I think that's it for today. Next time, I believe I will talk about derived junctions, in more details, and maybe we will start on some co-completeness properties, completeness and co-completeness properties of model categories. Maybe discuss homotypical limits and coordinates. Thanks. Okay, if there are no questions, then I guess I'll see you this Monday. Thank you all for coming.